Deep inside any modern computing architecture, the physical reality is dictated by microscopic copper traces pulsing with rapid light. At the center of this topology sits the central logic unit, executing calculations millions of times per second. But a processor operating in isolation serves no purpose. Its utility is entirely dependent on its ability to move the results of those calculations out to external components and receive new data in return. Looking at these architectural notes, we can see the historical engineering solution to this problem. Data leaves the processor via a bus, a rigid, dedicated physical data path connecting system components, and exits the machine through physical ports. In early personal computers, these were parallel wire paths strictly confined to the dimensions of a single motherboard. But as data demands scaled up, running discrete parallel wires for every peripheral created a severe physical bottleneck. The scale of modern data processing is outgrowing the traditional model of rigid, localized hardware buses. The local motherboard bus has functionally expanded into a data center-wide network fabric, changing the physical requirements of hardware architecture. To understand how we scaled up, we first have to map exactly where the traditional architecture hits a lull. This diagram illustrates the traditional hardware baseline. The immediate path out of the CPU is the system bus, which carries data back and forth directly to the local memory. When data needs to leave the core system entirely, it hits a routing intersection known as the bridge chip, which channels the data down into the host I/O bus. It is at this point that specialized hardware takes over. Various adapters plug directly into this host I/O bus: graphics cards, network interface cards, and storage adapters. Their job is to translate the system's internal data into formats the outside world can read. The terminology here contains an important historical contradiction. We still refer to this area as the host I/O bus out of sheer habit, even though modern hardware replaced those individual internal buses with localized networking long ago. The engineers had to make that switch because legacy parallel buses run out of physical space. You can only fit so many copper pins onto a motherboard, and parallel signals degrade rapidly over anything more than a few inches of distance. The solution was to replace those dedicated multi-wire parallel paths with high-speed serial networks, shooting data 1 bit at a time at incredibly high frequencies. By abstracting the physical bus into a localized serial network, the system detached itself from the physical dimensions of the computer case. The bus was now free to expand. Once data leaves those host adapters, it fragments. The unified flow of the system bus breaks apart into 3 distinct competing traffic paradigms. These 3 lanes are local area networks running the IP protocol, storage networks running the SCSI protocol, and cluster traffic running on protocols like InfiniBand. Let's isolate the storage lane. Historically, connecting hard drives required thick, rigid SCSI cables. These cables were expensive, inflexible, and severely limited how far away a disk could be placed from the processor. To solve the distance limitation, engineers decoupled the logical SCSI protocol from the physical SCSI cable. They created the Storage Area Network, or SAN. These notes diagram how a SAN operates. It takes the SCSI storage protocol and maps it onto a high-speed fiber channel network medium. The software trick here is crucial. As noted on the page, the CPU is completely unaware of the network. It still believes it is talking to a local, direct-attached hard drive via a physical SCSI cable. Fiber channel requires specialized, expensive hardware, so an alternative emerged, iSCSI. This takes that exact same SCSI storage protocol and wraps it inside standard TCP/IP network packets over common Ethernet. The advantage here is strict cost efficiency. Instead of building a dedicated parallel network of fiber channel switches, a facility can utilize its existing IP Ethernet infrastructure to move storage data. This encapsulation process tricks the operating system. The OS generates a local disk read command, which the hardware secretly wraps into a network packet, fires across the building, unpacks at the storage array, and executes. Think of this as a set of nested envelopes. Raw data is wrapped in a SCSI command, which is then sealed inside an IP network header, allowing it to route cleanly through standard network switches before being unsealed at the destination. Through this abstraction, adding petabytes of storage capacity is no longer a matter of opening a server chassis to install drives. You simply plug a new storage array into the network switch. Protocol encapsulation is the architectural mechanism that allows a small local motherboard to project its storage bus across an entire continent. That explains standard storage, but the third traffic lane, cluster computing, operates under much tighter constraints. This is where multiple machines pool their resources to act as a single supercomputer. In massive cluster computations, the standard Ethernet method fails, forcing the operating system to read, process, and strip TCP/IP headers for every single packet takes too much processing time. Every time standard network traffic passes through the software kernel, the operating system imposes microsecond delays. In high-performance computing, those microseconds compound into heavy bottlenecks. To eliminate that delay, architects utilize InfiniBand networks, which rely on a concept called Remote Direct Memory Access, or RDMA. Tracing the InfiniBand topology on this diagram, we see how the hardware connects. An application interacts directly with the network layer, routing from the CPU and RAM out to a switch. The key component is the host channel adapter, or HCA. The notes indicate exactly why this is critical. The application talks directly to the adapter and completely bypasses the operating system's network stack. By bypassing the OS kernel entirely, the system avoids the CPU overhead required to process network traffic. Memory from server A is written directly into the memory of server B. This creates a stark contrast in the architecture. While the storage networks we looked at earlier rely heavily on the OS to wrap and unwrap layers of protocols, cluster computing strips all software intervention away. To achieve maximum hardware speed, the infrastructure must completely remove the operating system from the data's physical path. We now have three distinct network lanes: LAN, storage, and cluster. But maintaining three separate networks with three separate sets of cables, switches, and adapter cards creates a physical routing nightmare across a data center floor. The enterprise engineering goal is consolidation, forcing all three distinct traffic types to travel across one single, unified physical wire. These notes document the initial attempt at consolidation, where Fibre Channel tried to absorb LAN traffic. The barrier is explicitly stated here. Fibre Channel had only rudimentary support for multicast and broadcast traffic, making it structurally unfit to handle standard Internet Protocol data. Since specialized storage hardware couldn't absorb the Internet, the industry took the inverse strategy, migrating highly specialized storage traffic onto the omnipresent, cheap Ethernet infrastructure. This resulted in FCOE, or Fibre Channel over Ethernet. Instead of building dual networks, storage traffic is packaged up and transmitted over the exact same physical wires handling standard local area traffic. This consolidation allows distinct data types, with totally different historical origins and routing rules, to merge into one unified stream. We began by looking at the microscopic copper traces of a single motherboard, struggling to move data just a few inches to a port. Whether it is a PCIe lane expanding outward, or a SCSI command wrapped in an Ethernet packet, the functional purpose remains identical to those old copper traces. The physical I/O bus has transitioned into a network abstraction, scaling until the entire data center functions as one giant motherboard.